So like, I've done like ahead of my like, so like sit there for like 45 minutes. Yeah, like my body is right more. Oh, you guys see like 5 minutes, right? Wait, they don't like. I don't know. What do you mean the senior phase? No, it's like
homework of the field for Chapter-15. I think that is a good break. Start level sometime, and then you come like to see your. Alright, now you will see the, so we studied, right now we are studying Chapter-15 about alcohol, diols, thiols. So we already see like first two different ways of prepare alcohol. Now this number three. Number three is the alcohol from generated from epoxide. Right? We were studying all in detail of epoxide. Epoxide is O with come from like those double bond initially, right? Epoxide, the simple epoxide is this, right? So later on we'll see like more epoxide. So this epoxide is symmetrical, two carbons are the same. And later on you will see epoxide is unsymmetrical, some other epoxide, and like those, right? So then we'll see different way of opening this triangle ring. Here we will see just use Grignard and organolithium. Grignard and organolithium, they should exist as like use basic conditions. In the basic conditions, and they will usually open the ring. If you have right now in the symmetrical, if unsymmetrical, so this organolithium or the Grignard, so they will attack the side that less steric hindering. Some other liquefier you can use them in kind of acidic conditions. Then they will attack for those you will see later. For this one, so it will attack the side that's less steric hindrance, and see that makes sense or not. If you attack the less steric hindrance, that means in the basic conditions it will not produce the keton, and so that probably will happen if in the acidic condition it will produce keton, and then you will attack those nucleophile will attack the more hindrance. Right? So there's a difference. So in these basic conditions, it can attack the more like a crowded place. Here we don't have those problems, so you are just starting with a symmetrical one, and then you can attack on either side. Right. So we see there's one example. This is the general equation, The example, as one example, we will take one Grignard, and I think the example on the leg nose is a little like long, and you don't have to use exactly the same Grignard. As long as you have a Grignard or organolithium, and you plus this O, And you will see that two steps because you have the Grignard. So the first step, you want to use this, the diethyl ether. The second step, you use H3O plus to like work up. And let's see, we start with 6 carbon, right? And you are adding on 2 more carbon. So now we have 6 and 2 more carbon, like that. And you will add at the end, you will have the hydrogen. So maybe here and OH. All right. So then that's basically the idea. You can see this kind of approach of prepare the alcohol, and you will get 2 more carbons and bring out the carbon chain or the organoleasing. So each of the following alcohol has been prepared by Grignard with ethylene oxide, which means the epoxide, the simplest epoxide. Select the right Grignard in each case. So both of these compounds is produced from this epoxide, right? And then you examine this guy. This can be prepared from this epoxide, then plus some of those Grignard. And so pretty much you can see this. Those kind of alcohol, if they come from epoxide, so they should have like 2 more carbon than your Grignard, right? And in this alcohol right now, we have this 2 more carbon beside the benzene structure, right? So what you can see is this can come from the ethylene oxide, the epoxide, and then this benzene ring. So this benzene ring has the metal, and here it should come from the Grignard. And this is one of those Grignard we were used in the lab. Similarly, this one you can produce from this. This is cyclohexanol, ethanol. Okay. This is the initial structure. So this will come from the epoxide and from this Grignard, and plus this. So this is our analysis. Okay. Now doing like the forward ratings, pretty much repeating what you saw. Just be careful with like the 2 steps process. So this metal, and we will take this Grignard. So we will see you will have 2 steps. I should write the reagents together. So I will put it right here. So plus this epoxide. Then what is the first step? Is use diethyl ether. The second step use H3O plus. Right? And you know what's the product? The product is that. So we have the benzene, we have methyl, and now we will have that 2 more carbons come from the epoxide. second reaction is similar. So you take the cyclohexene magnesium, let's say bromide, and let's say zetan, our structure like this. So this is our conformation, one conformation of the cyclohexene. And with this time, let's put our reagents together like this. And so you two steps. And you need to do like the one step in the diethyl ether. Then you work up with some of the acid. So I think this process is very useful because you can increase the carbon by 2 more. We did not do like too much reaction on the cyclohexene node, so therefore the chair conformation is still similar. You don't have to sort of the flipping of the conformations. Any questions? Next is prepare diols. Okay? And we are going to study two ways to prepare the vicinal diols. So the first way to produce the cis-1,2 diols from hydroboration of alkene. So you use the osmium tetroxide, osmium tetroxide, reacting with a double bond. So you first produce the cyclic osmate ester, and then the ester can be like reduced to like those vicinal diols. So this is the general reaction produce the osmate ester. And very interesting in the development of this kind of method. So initially, the scientists just take this some of those double bond and put some of those OS04 in it, and then they will put something like some of those reducing agents, such as NaHSO3, which is sodium hydrogen sulfide, and in that the sulfide is positive 4. Not really the maximum oxidation number for sulfur. Sulfur can be positive 6. Right? So it's kind of the reducing agent. It can reduce like this osmate. In the osmate right now, like the starting osmate, there are the OS is plus. So in this reagent, the OS04, OS is OS actually the oxidation number is plus 8. Plus 8. And then you have to reduce it using reducing agent. So initially the method developer is like you simply adding the OS04 into a double bond, you produce that. That is pretty stable. And then you add NaHSO3, which is reducing agent. Because here this sulfur oxidation number is plus 6, plus 4. So then your sulfur can be plus 6. But anyhow, so then you will produce something like those, so this osmate will break away. You will produce H2OS04, and then in this guy, your OS is plus 6. Right? So OS is kind of inexpensive, osmium inexpensive, and also like toxic. So then they find out some other way, not use like the reducing agent like NaHSO3. So they use some of those co-oxidizing agent. For example, you can use H2O2 or some other hydroperoxide. So if you use that, you can also like change this osmate into diols, but that can also save the osmate because the oxidizing agent H2O2 can oxidize this plus 6 osmium back into the plus 8 osmium, and then we can reuse the osmium as a catalyst. From the intermediate, this osmate, you can see the addition is on the same side. So it's a syn addition. Okay? Because it's a syn addition from the same side of the double bond, you produce the sort of the cis-1,2 diols. Let's see example that produce the cis-1,2 diols. Usually it's very easy to see the cis trans when you have the cyclic structures. So I just want to see that the process we talk about on the top, sometimes you'll see some book and give you the OS04 reagent, then give you the NaHSO3 as the other reagent, and then some book will give you those kind of reagent, but both processes will give you the same result. Just one is more like environmental, the sort of the green chemistry, and so your product is the same. Okay? You will produce sort of the cis-1,2 diols. So I can write that these 2 H, both of the 2 H were counting up. And then you will have 2 of those hydrols. So that indicating we have these two hydroxide in the same side, on the same side of the ring. This oxidation can also performed by potassium permanganate. Potassium permanganate is more soluble in like those aqueous solutions, and but less soluble in organic solvent. But it's less toxic and less expensive. It goes through a similar middle step. You produce this kind of transition metal ester. So then you will just hydrolyze this and produce alcohol. So you also produce a similar alcohol with like lower percent yield. So sometimes if you want to produce a trans 1,2 diol, okay? So what you do is use those peroxide acid and with epoxide. Peroxide with you first use peroxide and then you hydrolysis of those epoxides. So what you do, you are starting with some of those alkenes, and use peroxide change into process is change into epoxide, and then you will change those into diols. Alright, so you starting with those these alkenes, and here is a peroxide acid. So your peroxide acid will change this into epoxide. So this will be our epoxide, and so then this will very quickly hydrolyzed to the diols. So in the hydrolysis process, you still have this acid, but not peroxide acid, just acid. And H3O plus. So you will produce a trans. The trans, let's see the structure of the trans. Now this time I will draw one H up and one H down. So therefore this hydroxyl on this carbon will be up, then one on the other one will be down. So these are two different ways to produce the 1,2 diols. Any questions? Now this problem 15.5 is give the structure including stereochemistry for the diol obtained by dihydrogenation of cis-2-butane and trans-2-butane. So when we see the dihydrogenation, it means you are going to use the osmate. The other name produces the trans, that means you're going to use the acid-catalyzed hydrolysis of epoxide. So these two names, either is the hydrolysis of epoxide or the dihydroxylation of the alkenes. They both kind of starting from alkene. So if I have a cis-2-butane, let's say we have cis-2-butane, and I will draw the structure a little different than what you saw on the red nose. So I'll use a wedge and dash. So here is a dash, and here is a wedge. So this is our CH3, and here is our H, and here is our CH3, right? So this is our cis-2-butane, and you use let's say use the dihydroxylation. Remember the name is OSO4, and in some of those in like the peroxide, hydroperoxide, which is this structure, O and H. And in this tributyl alcohol, with some of those, with OH. Remember, if you use osmate, OSO4, you can either use reducing agent or some of those oxidizing agents. So it's sometimes confusing. How can you either use oxidizing agent together with OSO4? But if you use the reducing agent, that means you produce a lot of waste. If you use oxidizing agent, you will re-oxidize that OS with +6 oxidation number back into this OS04, so then you reuse it. Now the stereochemistry means this. Now we kind of never review what we learned in my chapter 4 or something. So this, if we imagine this plane, okay, so these two metals come to the front and two like H to the back. So your like oscillator can attack this plane from the top or from the bottom. So let's say we attack that from the top. From the top, and we were adding a OH, and we are adding a OH. So if we imagine you put something on the top, initially all this structure here, they all on one plane, and this plane kind of goes into the board like this, and then this OH will push both groups initially on the carbon-carbon double bond, liberalize downward. Okay? So therefore, you still have the H in the back. So H is here, and then the other H in the back there. Okay? And you still have the metal stick liberal to the front. And like that. Right? So now here probably you can see the stereochemistry very easy. You can sign the S and or the R configuration. So we have two chiral centers. This is the chiral center, this is the chiral center. And this is a typical program, you have two same chiral centers. They are the same chiral center. They are the same because each chiral center have the same four groups of something attached on the carbon. And this carbon has H or H metal, and then this carbon. The other carbon is the same. So those kind of problem usually will give you, the so-called methyl compound. Methyl compound means.
Can we review the R and S really quick?
Yeah. So very quickly, for this structure, our priority. You sign the priorities. Priority depends on atomic number. Priority according to the Kahn integral pre-log rule, right? So number 1, and number 2, number 3, number 4. Okay, so you put number 4 away from you. It's kind of your steering wheel. Okay? So these 3 your steering wheel. Then that H is the one that's under your board, under your dashboard of your car.
So still would be 1, 2, 3, 4 and up percent.
Yeah, 1, 2, 3, 4. So this way, so this is the R configuration for this one, for the left carbon. So here is R. Okay. And then you can examine this carbon. Okay. This carbon, let's see, on this side, that's 1, 2, 3, 4. Goes counterclockwise, your H back. So it's X. So you have RS configuration here. Now this, we call that is meso. Okay? Why is meso? Meso compound, which means you have 2 chiral centers, for example, or 3 chiral centers. And then,
it's going counterclockwise, right?
yeah, this is counterclockwise, not only
It
clockwise.
switches the R and S.
Yeah. And you also have to see the H, where is your number 4. If your number 4 is back, far away from you, then clockwise R, counterclockwise S, otherwise it's just opposite. Sometimes you need to view the number 4 is pointing to you. If the number 4 pointing to you, closer to you, you do the opposite. But anyhow, so this, even though you have 2 chiral centers, because you have a plane symmetry. What is plane symmetry? That means imagine you have a plane coming to the middle, your left side, right side, mirror image. Okay? So let's say we put a mirror here. The left side is the object, the right side is a mirror image. So those kind of planes are called the symmetrical plane. If your molecule have 2 chiral centers and the plane have a plane, so therefore you have meso. Meso is not optically active, so that means you don't not rotate your bond. And so therefore we don't have to worry about it. We come attack this from the bottom. You will get the same. Now the other one, the trans, you have to worry about that. Okay? But the program will just write one structure that comes from the tag of the from the top. Our program will write most of them. You do a similar. So what you do, just write the double bond, and you write. So this case we have a trans. So therefore this is C3. Have the H. Now here will be our H, and here will be our C3. So this is trans. Now you also use a similar reagent, right? So we'll use OSO4 and this perox hydrogen peroxide, and then you use the solvent in the same alcohol, and that's in some base. So what you produce, so you have the carbon, and that change into a single bond. Now let's take them, they both come from the top. Both OH come from the top. And as what we did before, so this will push the two bonds immediately on the plane, deliver like downward. And so you will have this H forward, then in the back. And then similar for this method. So lower and in the back. So then you will quickly assign the configuration. And so this time you don't have a methyl compound. The methyl compound, if you draw a plane here, so if I draw a plane here, so that I know the left side and right side a mirror image. Now this compound you don't have the mirror image. And priority for this one, 1, 2, 3. So here you still have the R. And here you also have R. So both are R. And that will come from your attack from the top. So that's what you get is attack the double bond by OSO4 from the top. So this guy coming from the top. And that guy can also come in from the bottom. Okay, so those are the feature projections. We'll learn that in Chapter-15. Now let's just see from the bottom. Okay? So let me change the color of the paint. Let's see from the bottom. OSO4 from below. So what you produce is single bond C, and OH here, and OH here, because they come from the same side. Okay? Now this will push up, so that C, that H will go up, and then this methyl will go up, and then this H over here up. And then that methyl on the left side will go up. Okay. Now you identify this configuration here is S. one way to produce the the diols. We already see the other way to produce diols. Any questions? Comments? No? Okay, now let's see the chemical reagents. We see the chemical reagent in early chapters. First, reaction of alcohol with hydrogen halide. So that means your alcohol will change into some halide. So it's kind of useful because sometimes you have like a lot of alcohol available, and you can prepare the halide. So here's one example. We have this M-methoxy benzyl alcohol, and you add let's say HBr. So we add HBr. Let's change back into this. Okay. I think that is more visible. So we still have this methoxy on it. Right. So what else you have? We will replace the Br on the benzylic position by the OH in the benzylic position. Okay. You will replace the OH there by the Br. Right. So this reaction is about how you change the alcohol into halide. And you can also change the alcohol into halide. Not only use the HBr. You can also use the sort of cyanyl chloride. Cyanyl chloride is so this cyanyl chloride is the name for the SOCl2. Say sometimes you want to use the cyanyl chloride, right? So if you have a double bond in your molecular, if you add in HBr, the HBr can add on to the double bond. So when you do this one here, if you use HBr, there will be a problem. Then you have a double bond there, right? So you don't use HBr. And what you use is this cyanyl chloride, SOCl2, in the paradigm. So then you will keep the double bond, keep the double bond intact, and you will replace the OH by Cl. So what they actually do, I think later on you will see the mechanism. This SOCl2 actually combine with the OH and change the OH into a very good leaving group, and then in the time this SOCl2 combine with the OH will produce a chloride. So then the chloride can do some kind of like SN2 and replace the OH. So right now we will just don't have time to see the mechanism. So similarly, if you want to replace OH by Br, you can use HBr, or you can use PBr3. PBr3. So PBr3. So you can see it like 3, right? Now this review is kind of come late because you see like in some of the homework in like Chapter-15, you already use the method, right? You want to produce a double bond, then the double bond change into dihalide, and then dihalide double dehydrogenation produce the triple bond. So in Chapter-9 homework you use this reaction already. It's kind of you already review what you learned in Chapter-5. So this is sort of the acid-catalyzed dehydration of alcohol. Okay? Yeah, we studied this reaction even before we studied alcohol in Chapter-5. Because in Chapter-5 we studied alkene, the double bond. So there we studied how we prepare the double bond, and this is why we prepare double bond. Now, when we studied this chapter alcohol, well, this is the chemical reaction of alcohol, right? So in Chapter-5, we use this reaction of alcohol as a prepared reagent method, and here we emphasize or review again. So okay, so this is the chemical reaction of alcohol, and this organic chemistry, this few chapters organized like this. So always have some of those overlap. So we have KHSO4, KHSO4, and then K. Now in the general equation, you just see H plus and then K, right? And here you write down one specific acid, which is not so strong as the sulfuric acid, right? So this is a little weaker, but still acid. And so what you will see is this OH goes away, and you will generate a double bond, this double bond, and you still have the Br. Now we have like a very stable double bond. But this double bond like this, it is conjugated with the bending. Okay, so that's the other one is conversion to the p-toluene sulfonate. The general reaction is you take some alcohol, reacting with p-toluene sulfonyl chloride. Okay, and let's examine this general reaction, see what happens. So in that p-toluene sulfonyl chloride, we have this H3C like that. And let me write the structure here, a little like clear, we can see that. And the sulfonyl is this part, which means you have a sulfur double bond to two of those, and Cl here. In the product, you will have, if I rewrite that part of the structure, and what we have here, so we have the method on that is so-called toluene. And you will replace the Cl here by the OR from the alcohol. So see the difference here? You start with this p-toluene sulfonyl chloride, this guy here, and I have the Cl here. And what you try to produce is replace this Cl here by this OR. And then I mean the Cl here by this OR. questions? So then this all these parts together, okay? All these parts together, and this become very good. It become like very good living group. Okay. Your alcohol, okay, initially have that your alcohol initially have that ROH. So this not a good living group. Okay. Now this part now become very good living group. So what do you think if I here use this cycloheptaner with this ketone sulfonyl chloride, and if you write that out, you will write that so Cl, then write this time on this side. So we have this sulfur here, and double bond, and this chlorine here, C3, right? So that's it. That guy writing with this, so I spread that out a little bit, and or you can just use this structure to imagine, right? But you have to flip it over because that's this OH on this side. But anyhow, so what you will see is this cycloheptaner. I missed a carbon. And now we have, I think, 1, 2, 3, 4, 5, 6, 7. We have 7 carbon and OH. Now you're going to replace the H by that this part. Ready? Okay, so the our directive number 5 is about some of those reagents we studied in the early chapters. Right? We can change alcohol into halide. We can change alcohol into so-called tosylate. The tosylate is a very good living group. You can use it to do some of those SN2 reagents. So number 6 is about reaction of alcohol discussed in this chapter. And first of all is conversion of alcohol to ethers. And you can take alcohol, put a little acid, and heat up a little bit. You will produce an ether. So one general reaction is here. If I rewrite here, so I will have 2 of those kind of let's say ethanol. Okay? And adding that H2SO4 is very strong acid, and heat to 140 degrees Celsius. What you get is the solvent you use in the lab. So it's diethyl ether. And you probably want to see some mechanism. So if I say the mechanism, tell you what you do, you should be able to get the step, right? So the first step is proton transfer from acid catalyst to the oxygen of the alcohol to produce the alcohol sodium ion. So what happens is, let's see, our alcohol has the oxygen on it, have 2 long pair of electrons. Let's see, the acid H2SO4, HO, and S, O2, OH. Right, so just write out this part of the active part. So you have seen the electron transfer before. If you want to see the initially, you have a 2 electron pair here. Okay? And then these 2 more electrons are put on this. And what we produce, so this is very fast acid-base reaction. Okay? Yeah, then you don't have even the reverse reaction, but this, according to the pKa, this reaction pretty much going forward. Okay? So you produce this O with 2H, and only 1 lone pair plus. So next step is the name. So the name here, SN2. So this part become a good leaving group. This is a good leaving group right here. So this is a good and weak. And SN2 you need 2 molecules. So you will take this O and here, so we have these 2 lone pairs, plus what we just produced, the intermediate. The intermediate has the O and has 2H and has a plus 1 charge. So what happens is, this will be our nucleophile come in, attach the carbon, and then this 2 electrons come onto this arsenic positive charge. So this will be a slow step. Okay, so this is plus 1, right? So almost there. What you do is get the final product. Just take the H part away, right? So I think I would like to use water, as we saw before. Water is the better base. Plus and H, 1 pair, and take water as the base. It's really long. And then this will attack this H, and then that will give you like this. And this version produce the final product by acid yeast. And you will recover the acid-catalyzed. Alright, any questions? If you have a diol, okay, and on the diol in the molecular, if the diol is like far, and you can have the intramolecular this reaction. Okay? So we'll produce a 5 or 6 member ring ether, cyclic ether. Okay? So let's see if I have alcohol like this. HO. Right? And if you add H2SO4 and with some heat, you usually prefer a 5-member ring or 6-member ring. And in this time, it produces a 6-member cyclic ether. questions? Comment? And on the basis of that three mechanism we just did for for ethanol, you can write a similar three-step mechanism for this cyclic ether. Okay? So the first step, if I tell you the first step is proton transfer or protonation, right? That means you will take some of those H plus. So now this time, even though we use the H2SO4, but H2SO4 is actually will protonate your water, so actually you can use this as your acid. Right? So now let's say we have this HO. Now let's add the electron pair on those oxygens. Okay? And we have water, we have acid, and we have water too. So this guy positive one charge. Okay? And then let's say this electron can come and get one of those proton with. So this step is fast. And you produce the HO. So usually you just protonate just one like those O, right? When you have two O, you probably have less chance to protonate both O, and also because if you protonate both O, you have two plus on the same molecular. So once you have one plus on your molecular, that plus charge is going to repair your H plus. So that's just protonate just one O. And you can rewrite this structure that is just getting closer to like what will be your final product, and you can rewrite something like this. And this will have the oxygen initially amide and have that. And then that has the oxygen that's already protonated. So we start with diol has a 5 carbon. So you can number the carbon from either side. If I number the carbon from the left side, we have 1, 2, 3, 4, 5 carbon diol, right? We call that a 1,5 pentane diol. Right? Now here you still have the 5. Right? 1, 2, 3, 4, 5 here. If you want to never know, so this is our number 1 carbon emitter in that chain look like that. 1, 2, 3, 4, 5 carbon like this. So now this carbon 5 has this hydroxyl. So this hydroxyl can attack this number 1 carbon. And then this electron can goes on to this water, and water will leave. Okay, now you can. Right? So now you can do that. If I rewrite again, so we have this few atoms here, and we have O, and we have H, and H, and this have a positive charge. Okay? And we have this O, I have 2 electrons there, and we have an H here. Okay? And let's see those reagents that we indicate on the top. Let's see these 2 electrons. So these 2 electrons can attack the carbon. Then the electron from the bond can go back on the oxygen. catechins. Plus H2O, right? But H2O is the leaving group from this step. Okay. So what we mean by the last step, loss of proton in the alkyl sign. Which proton will be lost? So we take this structure again, right? And now that's right here. We have this H here and have the plus here. Okay. So that means this proton, you are lost, you lost this proton. Okay. So what take the proton away is water. So water has long pair of electrons and grab that and give the electron back to the oxygen. Plus H3O plus. Okay, so the next reaction is S-terrification and also called the Fischer S-terrification. Fischer S-terrification probably is the most studied organic chemistry reaction. I remember one professor, when I was at college, he studied that this kinetics of this, like the mechanism, and see what is the effect of solvent. And in the 70s, 60s, yeah, he is very active with that research in those. So in all the following examples, what you want to see is keep like the mechanism in mind, and you will see like where the O come from in the ester, and the O in the ester come from the alcohol, which was this car was confirmed by a scientist in the University of Chicago, used like the O18 isotope labeling. And this reaction is reversible in equilibrium. So there are many different ways to make the reaction going forward. And you can use excess alcohol, depending on what is more valuable. Okay? But in this reaction, you use acid-catalyzed with liberal heat and reflux, and you produce this ester and water. Okay? So we will see this number of labeling where the O come from and where the H come from. I mean where the other goes. Okay? So this because initially we have the O is red and this O is red. So that O is actually initially come from metal. Okay. So we were like doing more practice from the mechanism. Then you will see it will clear why the O is coming from the alcohol. Yeah, we will see those mechanisms later in later chapters. Usually it's very simple mechanism. Right. So let's see the in the mechanism briefly, you will take those acids and protonate like that. Protonate that carbonyl oxygen here, and so adding like a proton there, and then you will have this alcohol come in, attack the carbonyl carbon, and go through a few steps, and finally you will get rid of that. So this OH work the leaving group left. So therefore, in the final ester, the O is come from the alcohol.
Is it from the alcohol?
They're from the alcohol. See here, we have this red O from this methanol, and you have this red O. So that means it comes from the alcohol. So therefore, let's use this. Write the structure of the ester produced from the following reagents. So what do you think you can produce ester from the first reagent? The first reagent you have the acid is propanoic acid, right? So let's see, propanoic acid has 3 carbon, and you have this here. Your ester should have O, and it should have that part from the alcohol. So alcohol has 1, 2, 3, 4 carbon. So this is the ester. Now if I change the pen, so this O here, so this red O here, it's red. So this red O here, either from what? Either from the acid or from the alcohol. This O here, in the ester, in the product, come from what? From this alcohol. So this is from this O. Now then by this O, and change the pen, and all the others. This is where this O comes from. So these two same O.
So where does it come from, you said?
From outside, this O comes from the alcohol.
Oh, yeah, that's right. Because you asked the class where did it come from, and then I said it's right.
Like that, you did. Right. So for B, we have the for B, we have a dibenzoic acid, right? P, 2 acid on the benzene, and we add in 2 methanol. Right? Now let me just put it here. The 2 CH3OH. So you have this OH and C carbon, and same on this side. So we will see adding acid and add heat. Right? So the question gives you this very, very complex formula. But you see, you still have 8 carbons, 6 H, and 4 O. So what it produces is you still have the benzene, and right? And then you will have this CH3, and then you will have this CH3. Now I leave that blank because I want to like emphasize again this where this O comes from. Right? So if I write this O here in this methanol as red, then you will see this O here is also red. Okay, so good. You can use like an acid with alcohol, or sometimes even easier use like not use the acid. In chapter 19, you will study acid is not that reactive with those kind of reactions. So like the ethyl chloride or anhydride, more active with alcohol produce acid. Even that usually people will do like take some of those acetic anhydride, you will see the smell very, very strong. And you take acetic anhydride, plus some alcohol, and we can prepare, for example, aspirin, wintergreen, and so this. You don't use really the simple acid, right? So for example, you take this, then your reaction condition is very mild. You don't use H2SO4 and heat, and sometimes your glassware is closed. So then you have acid, 140 degrees Celsius acid, so that's kind of very dangerous. So now this Cl is very good leaving group compared with water. And so what you produce is you still have this O and this carbon, and you still have this oxygen. And you have this product. So this product here. And then this product here is going to attach this isobutyl and we use O. And attach the first to the O first, and O will attach on the carbon. There's nothing yet. Here we go. Find out this one. So as it goes up, and then goes down, then O. Here we are. Right, let's see some with anhydride, right? Okay, so the last example is with ethyl chloride. We can use anhydride. With anhydride, for example, this anhydride, what you will produce is like this. So you will have this F3C, and it goes up, and like this, and this will give you the ethyl group. So then you will have this oxygen from the alcohol, and alcohol is this 2-phenyl ethanol. Okay, so plus plus the other part of the carbonyl become the acid. Okay? So become the acid, you can write the acid with the OH and CF3 power bond O. So that's the other product. Now let's do a ratio synthetic analysis. So I'll give you 3 esters. You need to identify from what alcohol and what acid anhydride. Or from alcohol with ethyl chloride. So either anhydride or chloride. We have 3 esters here. Okay? I think there's a few problems. Again, you want to practice and remember the oxygen will come from the alcohol. Okay, the first one is this. Let me rewrite this one so you can see it up here. You want to get this ester. And this ester has O and has this carbon, has CH3. Right, so what kind of alcohol or what kind of ethyl chloride can we use? Let's see, we'll probably do a continent bond in the ester like this. Right? So then we want to know that O will come from the alcohol, and the other part either from the chloride, ethyl chloride, or from the anhydride. So that's first from the chloride. So therefore, the alcohol should be the phenol. So the phenol like this. So this is OH. Right? Then if you don't use ethyl chloride, your ethyl chloride will be the acetate chloride. So it will be this O here and CH3 here, then chloride here. Okay, so I think that will do it. So these 2 compounds together probably use a little like pyridine. You don't have to use acid. So these 2 together and use pyridine. Next one. Okay. That's good. So I move that one there. Okay. And the same one, so you want to produce this. You want to produce this, as you write that like a zigzag way, easy to see. And you will start with, again, phenol. So this phenol, we're going to start in Chapter-15. Right? Now the anhydride, so this is anhydride. So you need acetate like you need acetate. So that means you can get acetate either from the acetate chloride or the acetic anhydride. You can get it from the acetate chloride or the acetic anhydride. Okay, now what about this? The B. Okay? Part B, let's move this one. And move this one somewhere. Well, there you want to produce the B, which has a structure benzene, butane. You will have this oxygen here and oxygen here. Right, so what do you think? What kind of acid or we will talk about chloride or anhydride and alcohol. Let's first identify the alcohol. What alcohol should we use? let's do a bond cutting, right? Cut the bond that has the between the carbonyl and oxygen. So therefore, we know we will have this one butanol. Now the acid will be clear, right? So what acid did we use? We did the first lab when we separated that the polyol number 5, right? The acid is what acid? The benzoic acid, right? So this acid we use in polyol number 5. But here you're not going to use acid, right? Here you use what? Here you use chloride. So the first is chloride. And the next one is using the anhydride. Okay? So that is HO. And plus anhydride pretty much just say another benzene. And so the anhydride will have this acid here, then this O, and then this acid. Right, so either this method will be able to produce this our product. In both methods, either use chloride, ethyl chloride, or the anhydride, you use the paraffin. And here you can also use paraffin. Okay, so what is C? C is this structure. So C, again, let me move this one over like somewhere. Okay, so what you want to produce is, that's not that one. Even though this have show you some stereochemistry, I don't think that is that much important. And why? I think that means you will keep some of those stereochemistry depending on what is your reaction center. So this O, and then you have this O bonding to the C, and bonding to the double bond O, and bonding to the C3. So that's our product. Stereochemistry here, right? And you do a bond cutting. That's the bond cutting between the carbonyl and oxidation. Okay? So therefore, you will see this is the product. So just move there. Okay? And what you say, you need this alcohol. Okay? So this alcohol has this spectral geometry. So you have a C3 on top of the ring, and then you will have this alcohol OH at the bottom. Right? And this geometry, why we have this geometry? Because this geometry has the hydroxyl and the methyl opposite. And here you still have opposite. So here, even though like in one step, you will see that SN2, but SN2 is not heavy on this carbon. Okay? So therefore, this carbon geometry is not a flip or not a change. So you still have the same geometry. Remember in magnesium, one step, use the oxygen attack. So actually use this oxygen attack this carbon here. So then you can use ethyl chloride. The ethyl chloride should be simple because it's just simply come from this here, like this. If you want to use anhydride, you take the same alcohol. So you will take the same alcohol like that, and the CH3 and OH. Now this time, you're not going to use the ethyl chloride, but you use the anhydride. Okay, I think now we'll take a break. Take a break. In the break time, you can take like a 5-minute break, bathroom break, and then you like a break. Each group will come forward and show your result, show your work for the quiz for Chapter-15.
That's what I used to eat.
Oh, so why am I eating those?
Yeah. I mean, it's hard to do that.
Let's bubble that one.
Oh, really? Cool.
Yeah.
Wanted to get it right there.
Dude, I was a jump like I wanted to throw it up there and I wanted to get snapped right there. I'll just stay there. I'll just run on the light. Yeah, I'd rather be like.
I actually went to the
Hi, YouTube.
So I mean, it's not a question.
Like 7 hours. Yeah, it's just more than that. Oh, it's more? Yeah, it's like 14 hours.
Like, big.
Worst.
I have never been worse. Oh, yeah, here's like, I'm gonna look at here. They have like,
Yeah.
these deals on. This is like a.
You gotta get your You're getting the bowls instead of the burrito. I did something to
That's fine.
You got it, Cuddy.
I was in the bowl with her tea on the bottom.
Yo, what is pudding?
What is that? I don't know, bro. I don't know.
I guess actually
I had an unfortunate cut.
That was bad.
That was an MRE cut.
Yeah.
Oh, I heard you. Just like talking.
Oh, yeah. I like stop like what you're
I was still like, it's class.
I used to remember how to act and
You tried it? You should do it.
This is
do
the
it.
test, like, yo.
I did my fair share of time though.
That was a good
I ran
one.
track and I did like
I love
I did track too. Did hydro?
because I lived in Rockford, they used to come up to me, the guys from the shoes that I'm there, because I'd be all covered up. I could not joke.
The hydrogen, you go up.
Shop was the YouTuber, bro.
Like 6'3" and jump it, and then when you jump that, you just go down. So I was like way down the whole time.
I know, I don't believe
They're
it.
not lazy, that was I jumped. You remember jumping high as a natural.
Like a lot of
Your legs sunk. That's it. That's all you need.
You don't have to bust that. Wait till it's
You just literally 7 pounds. It would be all water. It would be all water. It would be unhealthy. I was like sleeping in sweatshirts. Like, oh, nah. I had practice days on the way out. I'm losing all pounds of water in practice. No, I wouldn't do that. That's just too much. If I ever had to do that, I would just quit.
They like throw up right before they have to get
It's so unhealthy.
That's what I was doing before, like,
Yeah. You dehydrate yourself from a man and then you just drink the shit. But it doesn't make you feel good. Because you're already dehydrated and then you feel shit the whole day and what, you're gonna feel better in the bottle of water. Unless you had a day where it doesn't. I remember this one time. I was so dehydrated. I passed out on the last night. I had a sick day. And someone on the other, this is the most embarrassing one of my life. Someone decided that they didn't have like, I was 125 and someone was like, it's like, yeah, we're absolutely not this, so we're gonna have to give you someone 10 pounds of weight. I'm like, okay, it's easy. And then just like, wrecked me, because I so dehydrated. I couldn't do it. He wrecked me, he pinned me. Yeah, but like athletic. I would never do that.
If you start getting messages like all this,
Oh, you did? Yeah.
150, I made it all the way. This is my first time fighting tournament. Made it all the way to the final.
Literally, dude, you would just be hopping around. There's a black.
I actually checked it out. Okay, for this one, I said
Try to
it's
sweep on it.
so we're just going through like this.
Like, roll it back. Give it a tail. Tail is actually really good for your head. Have you ever heard of
I mentioned you. Like the last message, like there goes 20 days.
CTE? Have you heard of that? Oh, that's CTE. That's just so bad. Things like,
No, because they're gonna use it for Harvard.
No, nothing happens. Yeah,
Would you guys do like
We should group this line together. Who are you in that group? At least 4 person in my group. Yeah, I think 4 person in my group. We should from this three parts. Who's your group member? You have some group member?
you got it.
Group members? Yeah, you do group 1. So let's say always write your name, all your name on the word, so I know turn in, right? And turn in is one like those yeah, one, yeah, just one.
You don't have to write your, like, your speech or
Just group number,
you can just submit one.
yeah, submit one from club group, just submit one. So no, we submit in, you have to write your like group member name. Yeah? So your group starting. Yeah, all your group members will come forward.
I didn't write it.
Come forward. Let's start like 2 groups at one time. One group here, another group here. Your group right here.
Actually, I started writing from those.
Yeah, first question. Let's see, who are the second group?
I wanted both of them.
I hope it's
Out of 15.
Now you turn in just writing all your group members' name on one page. So now all 4 of you come here. And do the number 2, try the number 2. On here. Now give you more than one person in number 2. Give you more than one person in number 1, just write all the persons. All the answers for all the persons in number 1. And let's see, you guys, how many of you have 3? You get one more. Who want to join this group? You can, no, I will say, so this is group number 3. So who is going to join here? Just 3 of you? Right? Okay, so you are group number 3. So then just wait a few minutes. When we finish, you go there and present the number 3. Alright? You're number 4. You guys are only number 4. So number 4, you do number 4, do the question number 4. Okay? Number 5, do number 5. Number 6, do question 6. Okay, no, let's all come here and exam. If the question went by the dog. They come here, look at the question went by the dog. This is the question number 1. Okay. No, before we sit down, we are recommendation and you guys come to the front and make a
No, you can go up there and write it.
That's obviously
Wait, what's yours?
and then the last thing usually is like
Wait, so is it green or is it like double? Or is it like, is it literally like S or S? Oh, okay, so hybridization, that's it, okay.
I'll just write down these.
You guys already heard December 1, right? Yes.
Yeah, I was aiming for like a 507, 508, which would be like 88 percentile. Better than I thought I would. Yeah, the pretty circuit okay.
What? 35 is
That's like 507.
Wait,
The highest score you can get is 508. So like 501 is and it kind of goes to 508.
It's like a signal, like, is it all you want to if I have to explain like hybridization, what is it? Electronic, I don't like Before B, because there's two highlights or spread it out.
So I was like freaking out about yeah. He does it every like.
First day you give it like
Yesterday when he picked like,
That was the only question I had.
They just go all the way around. I know. No, I was really like.
so you have the science sheet basically, I don't have to worry about that. 625, as soon as I get down now.
It's all about normals.
I just like, mine is probably not gonna get 0, so best to get like 80.
Let's do one by one. Everyone get a split up. Group number one. Group number one did it together. Okay, so everyone sit and just listen, see their explanation. Okay. Group number one, come forward. All your group member. All of you.
I was just gonna go play drum.
Alright, so we had, number 1, and it's just asking which one is shielded. So we explained that this right here, this,
Talk to you. Hi.
okay, oh, do you want me to, okay, so.
We said that this one is the most shielded, this carbon is the most shielded because it's the bulkiest. And so we wrote that has the smallest delta value. That this right here is the least shielded because that has, because it's the closest to bromine. And it has the largest delta value.
Yeah, so the most de-shielded will have the largest delta, right? And that H you indicating the most have the largest delta, the most de-shielded or less shielded. That's because it's closer to the Br, right on the carbon with Br. And I asked like my member, what will be the next largest delta? What means what will be the next Z1? Right? Why not the one on the left side which is methyl?
Why not this one?
Why not that one the next largest delta?
Well, the one with that's the second most shielded would be here because it has both of these sides, like, but
Both,
rather than this one would only have this.
yeah, depend on the carbon, right? So the more carbon you replace the H, carbon is more electronegative than H. And that means you pull the electron away from the carbon, so it's de-shielded that H. Methylene, so the one you want into the methylene. Very good. Any questions?
What's that?
Oh, so it's the H by the bromine that's the least shielded?
Yeah.
Yeah.
Yeah,
Okay.
because it's less electric.
Dude, I just swore I saw the freaking.
Yeah, you want to do it.
Yeah, do it.
Dude, I
Remember, hey.
It's all wrong.
Yeah. Okay, so for 8, the main thing we use is just the HDI and using the formula C plus 1 minus half times H plus X minus N. You guys can see it written out here. So the HDI is 2, which indicates that you have a double bond and a ring, or 2 double bonds. And then based off of the formula, which I'll write up, it's C6H10O. We just found the structure that works with that, and then with the peaks also.
So if you write a structure like this, a cyclohexane, right? How many different carbon we have? So that means we should have 4 signal in the carbon 13 AMR. Do we have 4 signal? Everyone know the equation number 8, right? So if you think this structure is cyclohexane, you should have 4 different carbon. And then you just check back, do you see like 4 signal in the carbon 13 AMR? So we have 4, right? So that means it's probably okay. And then let's look at that. Look at this AMR, that proton AMR. Proton AMR. How many signals there? We have what? 4H and 6H, right? Not very clear. It looks like we only have 2 signals. Should be 3. I think it should be 3 signals, right? And yeah. That's good. So you have 3 signal for the H and MR, and we have 3 type of H. What are the 3 type of H? Well, what is the first type of H in this molecular structure? The triplet or doublet, not clear. Let's see, you see the one signal to the 11 moles is above like 2, right? So where the signal in the H and MR that are above 2, the delta more than 2, where does the more than 2 come from? Come from what H? Closer to the carbon near, right? Yeah. So therefore, there you see we have 4H. See the integration, you have 4H. You can draw that 4H out. What is that 4H? Have the signal has like more than 2. The delta more than 2. See that signal, right? You have 4H. The integration has 4H. Where are the 4H? Where are the 4H? Did everyone see my question? You see the 4H in the H and MR, there is an integration number. There is a 4 on the signal that has the delta larger than 2. And I want them to draw out that 4H. Let me draw all the H. Where the 4H give you the delta. So what do you think of that 4H? Which 4H give you that signal? Did you see that signal? Did you see that the delta like more than has the delta more than 2? See this MR, this one has integration number 4. What? Here. So this signal right here looks like a double label, right? So this have a delta larger than 2. This temperature was never 40.
Yeah. That, like that. 4, 8, 4.
Yes, yes.
6.
Go 4. That's serious. Together, I think I'll see like all this,
Like 6 in my 4th one.
Because you asked here, how many signal?
Okay, very good. So who is the number, the number 2, right? Yeah. And now let us see question number 2. Question number 2.
Alright, so for this one we're given the structure and told to number, like match number with where it goes. So we kind of use these values over here to base off where to assign the numbers. So since these are on the ring, these would be between 6.5 and 8.5, so it's 7.2, and it goes over here, so it's far, so it's more shielded, so it'd be a bigger number. And then this value over here, the CH next to the T double on O is between 2 and 2.5, which is over here, so next to the T double on O, so that's 2.0. And this carbon is the benzylic carbon, so it should be 2.3 to 2.8, but since it's by the O, it's going to become less shielded, so it becomes 5.
That's a good explanation, right? Yeah, very good.
Cool.
I think here is also okay. So who is number 3?
So it's 1 bromobutane, which leaves us with hydrogens in 4 spots. And these hydrogens are all, they connect to one another, so we've got 4 signals that this would give out. The next one, B, is 1,1,4-tribromobutane, so there's 4 bromos, and it creates a different structure. So you got 1 bromo here, 2 bromos over here. So that means that you can't reflect it or anything. Again, we've got hydrogen, 2 hydrogens, hydrogen, and 2 hydrogens, making 4 different groups that would show up on the signal.
Okay. Yeah. Good. Number 4. Number 4. Who is the 4? You are prepared.
So for number 4, it has described the appearance of 1H NMR spectrum of each of the following compounds. How many signals would you specify, and how many peaks will each signal split? So the first one was 1,2-dichloroethane, and the
protons of 1,2-dichloroethane are all chemically equivalent, which means like they all have the same chemical shift. So the NMR would have consist of one single like sharp peak, which means that it has two signals.
No splitting, right?
Yes.
There's one single sharp peak.
Yes, no splitting. No splitting.
And for 1,1-trichloroethane, these ones, this has two signals and they also have the same chemical shift, and there's no splitting as well on this one either.
You see no splitting either? 1,2-trichloroethane.
There are like two, we have triplet and a doublet for.
Oh, you have a triplet and a doublet, right? This is called splitting.
Oh.
Yeah. So we have a triplet. Yeah. Very good. So which one?
Did it ask us to put triplet or doublets? Because
So
it
your
didn't say the
question is
problem.
Yeah.
kind of
Yeah.
confusing, because it says
Yeah.
how many peaks
It
will
doesn't
each
ask for
signal
triplets
be
or doublets, so
split?
you don't.
Yes, that means you identify if the signal split into three, you call that a triplet.
Determine if the signal splits.
So you're asking for that, because.
But it asks
Yeah,
like the number of
So
peaks.
The peak is like those, if those three triplets together, pretty much come from like one group of age, and depend on how many
I
age.
understand, your question, so if what I put there, one peak and split into three triplet.
Actually,
answer.
Does that mean you can-
So I don't know what to say. Like, the answer could be
Okay.
If
Okay, I think your group is right now. Now, do you know like which of is the triplet will have a larger delta or the doublet will have a larger delta? Which one will have a larger delta, the chemical shape?
A larger delta?
Yeah, which one will have a larger delta?
Oh,
Yeah.
The triplet.
one that's the lowest electric net.
The other one has no electronegative atom on it.
Yeah.
Yeah. Yeah, the triplet. Yeah, okay, so that's
But so then, how does that go to the number of peaks though?
the number of peak depend on the LGS and the equivalent age. You see that you have that one age on that dichloro metal, right? So there's one age here, there's two age here. So the LGS and according to the N plus rule, so this age here, so this age here, the signal are going to be split by this two age. So 2h plus 2 plus 1 is 3.
There'll be a split. So that is
The opposite. So these two split, this one is triplet, and then vice versa. This only one here. Yes, split into that.
So the triplet has how many peaks?
The triplet are going to have 3 peaks.
Okay.
So this signal from this age looks like this.
Yeah. That's doublet.
Double is just, both of them double is equivalent. So then the chemical shape, so here the large number, right? So usually you have like something like 0 here on this side, and you will have something like those, for the HMR, you probably get like 12 or something to the middle.
And then for this one, for it to be 2 atoms.
This one is one.
Just one.
Just one. Just one sharp signal, that means 0 here, right? 0 here comes from the SiC34. So 0 usually don't show any signal. That's just one signal somewhere there. Okay. Okay, group of 5.
Yeah.
So number 5 is just there's two different structures, and you have to figure out how many peaks there would be and how many signals there would be. For the first one, the benzylpropene, or propane, propylbenzyl, there's 7. That's because there's 2 unique peaks on the benzene ring, and then two set of peaks that are actually equivalent. So the Y and Y and the X and X have the same splitting pattern, the same chemical shift, so those are not unique. So these are all unique, so that combined is going to equal 7. On the second one, it's just non-unique signals, none that are equivalent. So there's 3 different ones for the methyl groups, and then 6 different ones for all the ones operating.
Yeah. So 9 and 7, right?
7 and 9, yeah.
7 and 9. Yeah, that's good. I think usually the carbon 13 and MR, you will see the signal is very clear. And you will see which one will have a higher or the larger delta, the chemical shape.
Which one will what?
What the carbon will have a larger delta, the chemical shape.
Larger delta.
You can use the table, like the table. I think the table will tell you usually those the carbon on the bending ring, right? Or the double bond will have a larger chemical shape, right? So your first one have a 7 signal, and you will have a 4 signal kind of those 4 carbon from the bending ring. Will have at a place and the larger delta. Get it? Then other 6 from the 9 signals will be on the left side. Alright. Any questions?
You said the second one has a higher?
The second one similar. Second one, you have 9 signals. Altogether 9. 6 of them will be at the higher place.
I'm talking about the 6 that are just.
The 6 come from the 6 carbon on the main ring.
Yeah.
Right? Yeah. Okay, what number now? You did 7, right?
So 6 asks you to label this compound with the chemical shifts given, and those 2055 and 157s. So carbon X is like sp3 carbon, and so is Z. And so you just have to figure out which one has a higher electronegativity, and that would be Z. So that would get 55, and then X would get the lowest one, which is 20. And then Y, since it has the hybridization of sp2, it would get the largest number, so it gets 157.
Okay, you see Z has the second largest one. Right?
Yeah.
Why does Z have the second largest one?
Because it's more electronegative than X, but it doesn't have a better hybridization than Y.
Well, who is more electronegative than X? I mean,
Z.
Z actually is the same carbon. They are all sp3, right? See, the Z means those carbon. I think Z carbon is sp3. X carbon also sp3, but the Z is closer to an O, right? Oxygen is more electronegative. So if the atoms are the same, you compare what is the adjacent. If carbon attach on oxygen, then oxygen, like what we saw, is very similar as the chlorine. So chlorine is more electronegative than will pull the electron away. Alright, I think that's it, right? So the number 6. The number 7, Martin.
So for number 7, the top graph is 3 bromopropylbenzene, and the bottom one is 1 bromopropylbenzene. So the top one has a strong absorbance at 91, which is the bromopropyl group, and the bottom has a strong absorbance at 169, which is the BR that's directly bonded to the ring.
Draw the structure for the 2 molecular and see why we have that 2 signal, 2 spectrum. Right? Yeah, draw the 2 molecular. can explain, right? So you can explain that the spectrum on the top and the spectrum at the bottom. Why is the first spectrum is for your molecule on the right?
Yeah, because the BR is not directly bonded to the ring, so it's not going to show any intense absorption.
That's the base peak, right?
Yes.
Everyone know what is the base peak? What is the base peak in that MS? The highest peak. So the first spectrum, what is the number? What is the mass Z ratio for the base peak in the first spectrum? What's the mass Z ratio? 91. Right? And what is the mass charge ratio for your base peak for the second spectrum? 169. Right? And the base peak comes from the fermentation of the ion that is most stable. Right? So I'm writing what kind of, I saw you draw the structure for the ion, what kind of ion we produce that is most stable, produce 91 or the 169.
The 91 is like a 7-member ring and it doesn't have a bromine on it.
Very good.
Yes, and the 69 is the same, but it has a bromine on the 7-member ring.
Yeah. Kelsey?
No, just a statement to help people out. When you're looking at the two and you're trying to decide which one's which, you can tell that the one on the bottom is the first one on the option due to the fact that you've got two main peaks all the way at the end for your base peak, which means that it's got a bromine in it. So you would know that it's the first one.
Yeah.
Yeah.
Excellent. Okay, I think this is about this quiz. Well, see, we will take this quiz for chapter 14, right? And do a seminar. So when you turn in, just one group will turn in one page, and make sure all your group members' name on the page. Just turn in one like